Okay, the next tool I'd like to introduce is the cylinder dial bore gauge. Now this tool allows us to accurately read the dimension of the cylinder from its original point measured in the engine up to and beyond its maximum bore specification that the manufacturer lays out. Now their maximum specification will be the worn permissible limit. So if it is telling us that our maximum limit is 5 inches 122 thou, that means if we read that measurement or beyond on this gauge, that the cylinder is actually defective and cannot go back into service. At that point, it would be replaced because it's beyond the maximum amount of dimension that the manufacturer allows. So talking about the tool itself, we have a serrated edge here on this tool, right in this point. This allows us to hang on to the tool so that when we're measuring, we can move it in and out of the cylinder, up and down the cylinder, and we have to have a bit of finesse when we're working this tool. A lot of the times what technicians make a mistake with this tool, because it is a dial bore gauge and it's only reading on the scale half thou increments up to 25 thousandths of an inch positive, or pardon me, 20 thousandths of an inch positive or negative on the scale. So depending on where you sit the measurement and calibrate it, it'll read either positive or negative, and again up to the maximum diameter that the manufacturer permits. So we have an anvil face on. We have the anvil face here that when we move that, it allows the scale at the top to rotate. This is relative to the movement in the cylinder as we rock it back and forth and move it up and down in the prescribed areas for measurement. In the package itself, or the container that it comes in, it tells us that we use gauge points and the numbers that we use relative to either the metric or to the imperial measurement for specification of that particular cylinder. Okay, the manufacturer, this one engine in particular we're looking at is the Detroit 60 series engine. And the manufacturer prescribes a method of how we're going to go about doing this. It gives us dimensional measurements across two different axes, which is basically going to be the major and minor thrust area, and then of course the front and backwards movement of the pistons in the bore. Now the manufacturer also wants to make it relative to the movement of the piston rings in the cylinder bore. So it gives us dimensions at A, at B, and at C to determine how far that piston is moving based on ring travel. That's the area that we're going to get the wear. The cylinder wears in 3 positions. It wears at the very top of ring travel, where we have the most amount of movement. So the piston comes up under compressional loading, goes over top of neutral dwell, and then comes down under combustion loading. So that piston at the very top rocks through neutral dwell. And neutral dwell is described as the number of degrees of crankshaft rotation that the piston remains static. So when that piston goes up and stops momentarily until the crank pin moves and comes back down, think about what happens when we introduce RPM and loading. So now the piston moves down to the very bottom of its travel, and at the very bottom it also stops on neutral dwell, has to move across the crank pin, change position of the piston, and then allow it to start moving back up. So at the very top of piston travel, we have neutral dwell where the piston rocks, and at the very bottom of travel, at bottom dead center, the piston rocks again, going across neutral dwell. So we get a lot of wear at the very top, subsequent amount of wear at the bottom, and the least amount of wear occurs typically in the very center of cylinder travel. And that's where we have combustion loading and compression loading not as high, and RPM also has a factor involved in there, and overall cubic inch displacement. So as the cubic inches increase, the friction load increases also. So the manufacturer tells us on this particular spec sheet that we can have no more than 5 inches, 122 thousandths of an inch. Okay, taking a look at the cylinder out of a 60 series Detroit. So just talking a little bit about the cylinder in particular, we have our liner O-rings down here at the bottom. One that is missing is the coolant crevice seal, and it's a very large one. The very large seal helps seal the coolant into this area. And the second oil ring also here works in combination capacity with the coolant crevice ring, and this works as a backup for the coolant. So if the crevice seal for the coolant system fails, the backup ring prevents coolant from getting into the bottom end. Now, vice versa, we have an oil seal on the bottom that prevents lubrication from the bottom end of the engine from coming up. If this seal fails, the second seal works in combination capacity to help prevent oil from getting up into the cooling system. Now, at the very top of the cylinder, we also have a relief area. And Detroit, what they do is they have in their cylinder blocks a small coolant passage drilled on the adjacent side of where this liner sits in position in the block. That allows coolant to flow around this particular area and back out through the cooling system. What that does is it provides an additional amount of cooling above piston ring travel, which is right around this area. So from there to the top is where we're going to generate the most amount of heat from compression loading and combustion load. So what happens there is if we have that extra volume of coolant running around the circumference of this liner, it helps absorb that heat and carry it out through the cooling system to the radiator. That helps keep the temperature of the liner down, helps remove some of the heat loading at the very top of that piston. Pistons typically only absorb about 20% of heat loading unless it's a manufactured design based on a molly-therm piston, which is a molybdenum thermal piston, or it may be a full-floating articulated piston, which allows the skirt and the head to move, which decreases some of the heat loading. So when we talk about this cylinder, what we're looking at now is how this cylinder is measured for its dimension to find out, can it go back into service? Now, probably in the camera light, you can see that we have a good crosshatch pattern on this cylinder. And that's supportive of having good functioning clearances in the engine with the piston running. If we did not have those correct clearances, then we would see a lot of scarring, and we may even see some heat loading. We're going to take a dimension of this cylinder, and we're going to set it to the dimension that I already have established here. Then we're going to read beyond that measurement and hopefully not beyond manufacturer's specification, which we already established at 5 inches, 122. So again, I'm going to go in and just double check the dimension using a couple different tools. And we have 5 inches, 117,000. Okay, now the manufacturer says that this is a discard cylinder at 5 inches, 122 thou. So we still have a little bit of a buffer zone there. It's